Hi everyone, in this video we're going to take a look at separable differential equations. Before we begin learning how to solve them, let's take a look at a sample separable differential equation. And we'll start with a fairly basic example which you should probably have solved in the past. dy dx is equal to x. Let's take a step back, let's just look at what this means. dy dx is the first derivative of function y, right? So you can write this as y prime, that's the same thing as the first derivative of y, is equal to x. Why don't you pause the video, give this question a go, see if you can find the answer. Of course, there'll be multiple answers, it's a family of answers, but see if you can just find that family of functions. And the solution here is fairly straightforward, and we're going to see why this is straightforward, and we're going to see how we can use a similar straightforward approach for a much broader classification of functions, which we call separable differential equations. The way we can approach this is by multiplying both sides by dx. This will give us a dy on the left hand side. This becomes x dx. The next step over here is to do the reverse process of differentiation, which is what we have here with a dy and a dx. So we're going to go ahead and integrate both sides. That will give us the integral of dy on the left. And over here we have the integral of x with respect to x, as denoted by the dx. How can we solve this? Well, the right hand side should be fairly easy. We know this, we've done it before. It's x squared over 2 plus c. Remember to add the constant c. Technically, you should add the constant to both sides when you're integrating both sides of a differential equation. But since there'll be a constant on both sides, you can bring them both onto one side under a new constant. So we're just going to skip the plus c1 plus c2. We're going to skip that step and just make it one constant over here. The left hand side, it's actually not any harder than that. It might look a bit tricky because you don't see anything in front of the dy, but you can always put a 1 in front because it's just 1 times dy. And when you're integrating that, that will just give you a y. Right? It's the integral of 1 with respect to dy, that's just going to be y. So we have this, and that's actually all it is. If you want to verify this, you can take the derivative, right? So if you take the derivative of both sides, you'll get dy dx on the left, right? You're taking the derivative with respect to x. Over here, the constant c will never have, its derivative is always 0. So that doesn't matter. The derivative of x squared over 2 is going to be simply x, and then you can see that that matches with what we were given earlier. Why was it so easy to do? Why was it such a simple thing? Well, we could get it into this form. We could get it into some function of y. Over here, the function was extremely simple. It was just a 1. And over here, we were able to get it as some function of x dx. And over here, the function was a bit more complicated than 1. It was x. But you see the point. We were able to get it into something, some function of y dy and some function of x dx. And then we were able to integrate both sides. And that's called separation. Let's take a look at a more general theory. And what a separable form really looks like. So I'm going to go with lowercase a of x dx plus b of y dy, and let's just say this is equal to 0. Okay, so this is now a separable equation, and we're going to see why. You might already be able to see why. The reason for that is because you can just subtract this from both sides or subtract this from both sides, and what you're going to end up getting is something that looks very similar to what we had before. Remember, the negative comes because we're subtracting from both sides. And you see it here. We've got a function of y dy is equal to a function of x dx. The negative, you're going to put that into the a of x. And now what's the next step going to be? Well, just like we did earlier, we're going to integrate both sides. Again, we're going to keep the negative inside just so you see, but you can also take it out of the integral. Now, of course, if you're actually given a function b of y and a function a of x, you'll be able to integrate both sides and solve it. This is just a general way of doing it, so there's no answer that we're going to get over here, but that's how you approach it. For the example question that I take, I'm going to be using this book over here. I'll be using this book for probably most of the videos in the differential equations course here. Elementary differential equations and boundary value problems, Boyce and De Prima, 7th edition. I don't think that should matter too much. So let's just take a fairly simple example, again, not too difficult. This is the first example in the book, and it goes like this. So we've got the left hand side as dy dx. And remember, it doesn't have to be in that form, a of x dx plus b of y dy. It doesn't have to be in that form right away. You have to take it there, that's your job. And then this is equal to x squared over 1 minus y squared. Right, so again, what we want to do, we want to make this a separable differential equation, which it already is. We just need to get into that form that we saw. Then we want to integrate both sides and get the final answer for y, family of functions. So why don't you pause the video, take a minute, work through it and see what answers you get. And I'll start now. So the first thing we want to do, we just want to multiply both sides by dx and by 1 minus y squared. The reason for this is that we now get this on the left hand side. This is a function of y, 1 minus y squared. Remember to keep the brackets because 1 minus y squared dy is not the same as this at all, and that will make our work a bit more complicated actually. When we multiply by dx, we get the right hand side of x squared dx. What's the next step? Well, the next step is the same as in all examples we've done so far. We just integrate both sides. So we're going to go ahead and integrate. Again, remember to keep the brackets around that. The right hand side is just x cubed over 3. Again, remember to add the c. For you, again, as I said before, you can add the c to both sides, but you only need to add it to one because it's the same. If you add a constant to one side and the other side, you can subtract one of the constants from the other to get a new constant. And so instead of doing all that work, just put one constant on one side. The left hand side, this is just going to be y minus, this is y cubed over 3 is equal to this. We want to get it in terms of y, and this is known as, okay, I'm going ahead of myself here, let's just get everything onto one side. Let's keep the constant on this side. Let's multiply everything by 3. Okay, I'm going to call this c1 because you'll see why. We're going to multiply everything by 3 to just kind of simplify it a little. Now we have negative y cubed, so I brought that over there, plus 3y, as I multiplied by 3, so this becomes x cubed. Now we're subtracting this, so it's minus x cubed is equal to 3c1, right? We're multiplying by 3. We can just call that a new constant of integration, a new one. So 3c1 is going to equal some other c. If you want to make this look a little nicer, if you want to remove the negative signs or whatever, we can change this to c2 multiplied by negative 1. Now it becomes y cubed plus x cubed minus 3y equals some other c. Again, notice that c1, c2 and c are not the same. c2 is 3 times as much as c1, c is negative c2. So those are changes that we made, but because it's a constant and it's always going to be a constant, we don't need to write like negative 3c1. We can just keep it as c. And so this is our answer. Now this over here is an implicit solution. It's implicit because it's not explicitly in terms of y. Right? We see y cubed negative 3y. It's not y equals some function of x. So this is implicit. If we wanted something explicit, we had that in the very first example we did. If you recall, it was y equals x squared over 2 plus c. This here is an explicit solution because it's y equals something in terms of x. It's explicitly defined in terms of x and some constant of integration c. That's basically what we do with separable differential equations. That's what a separable differential equation is, how you can turn it into that form, what the next steps are, integrating it, and then just kind of briefly touch upon the differences between implicit and explicit solutions. So that's what we'll cover in the first video. In the next few videos, we'll do some slightly more challenging examples of separable differential equations before we move on to the next topic.